Now take a look at what happens when we talk about complex and finite length. And these are the kind of signals that you have that we'll be working with in MATLAB a lot. And you're wondering, how does the complex part come in? That comes in once you start to get into the frequency domain. And just like when you took the Fourier transform of signals back when we did EE430, and you took a real valued signal, and all of a sudden it became a complex signal in the frequency domain, that's why we're dealing with, that's where the complexity comes in here. But you're still dealing with finite length signals, and that adds a wrinkle to it. And in particular, we're going to say these signals exist between 0 and 1 less than n. So in other words, their entire length is n, with a fence post including that 0 signal. And we're still going to talk about the signal can still be divided into 2 parts, and still, the signal can still be divided into 2 parts. But now the part that seems even, is even-like, is going to be called periodic conjugate symmetric. And the part that seems odd is going to be periodic conjugate antisymmetric. So in other words, by making them finite, we've had to introduce this new P in front of an area that did not have that P up here. And let's talk about what periodic conjugate symmetric means versus periodic conjugate antisymmetric. And I'm going to first just write down the definition, which will look kind of weird, and then we'll break it down. I'll give you an intuitive understanding of what it means, and then we'll go back to the math. It looks almost like what we just discussed, with the exception of the indexing. And the indexing has that modulo operation. And you've probably been introduced to modulo arithmetic in your discrete class, but I'll review it here. Again, it's just like the periodic conjugate antisymmetric. It's just like conjugate antisymmetric, but it adds that same weird modulo arithmetic indexing operation. So let's talk about what this means intuitively first. And why do we even have to introduce this idea about periodic? And why can't we just keep it conjugate symmetric? Here's an example of a very simple finite length signal. Should have probably done that in blue to keep it consistent. It is non-zero between, it is non-zero in that area. So it has a length of 3. Why can it never be symmetric or antisymmetric? We want to break this thing up into even-like and odd-like finite length parts. Why can't we do that? For this finite length signal, why is it not possible to break this up into a conjugate symmetric part plus a conjugate antisymmetric part, where both of these are finite length, 0 is less than n is less than 3. Why is that not possible? And by the way, since it's not, this isn't a complex waveform, this is a real waveform, that's the exact same thing for purely real signals. X conjugate symmetric just becomes X even. And X conjugate antisymmetric just becomes X odd. So once again, why can't we break this finite length signal up into an even part and an odd part, where both even and odd parts are finite length on the same area as the original waveform? Intuitively, what can it be done?
Because there's no reflection around the y or x-axis.
Yeah, exactly. You can't reflect it around if you try to reflect it horizontally, you end up not having a finite length signal between 0 and 3. Now, as long as we allow it to be a non-finite length signal, non-positive index only finite length signal, sure, you can break it up into a real part and an odd part, just like we did above. But if you're going to limit to signals that are finite length, and when we talk about finite length signals, although technically you could have values that are finite length signals less than 0, I'm really talking about signals that you're going to put into MATLAB where the indexing begins at 0. And so since you can't flip it, you can't do it. So instead, what we're going to do is we are going to duplicate the signal over and over. We're going to create something called its periodic. I don't know if it says this in MATLAB, in the Mitra text, but it's true. We're going to create its periodic extension. We're going to go forever in this direction, and then the same thing in the other. All right, so now that we've got this, now we created this periodic extension. There's your P. And now we're going to go back to the earlier things. Let's find its conjugate symmetric part or its conjugate anti-symmetric part. And since it's purely real, we're just going to take it's the same thing as find its even part and its odd part. So let's compare these guys. And I've got a little bit too much red now. But you will pair them up with +2, -3, +3. It'll come out with a new waveform. That's its even part. So let's break this waveform out and find its periodic conjugate symmetric part, which is what we think of as the even part. So the center part will stay unchanged. And if this was 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on, the center part will stay at 1. And now this is going to be, according to our equation up here, the average between x of n and x of minus n. So our 1 value will be the average between x of 1 and x of minus 1. The average of 2 and 3 is 1.5. Similarly, for a 2 value, it's going to be the average of x of 2 and x of -2. So it's going to be the average of 3 and 2, which is also 1.5. And if you continue to do this, 3 is going to be the average of 1 and 1, which is 1. And if you continue this through on both sides, you'll see that this also repeats on ad infinitum. And then you just extract one section that doesn't repeat, which will be the same as your original waveform. And so therefore, your periodic conjugate symmetric portion of this waveform is equal to 0, is equal to 1, 1.5, 1.5. And you can do the same trick to find the periodic conjugate antisymmetric. So any questions about how to practically find the periodic conjugate symmetric or antisymmetric portions of a finite length waveform before I go into what the mathematics means?
Would those 1.5 be actually 2.5?
Did I? Oh my goodness, yeah, thank you. I managed to take the average of 2 and 3 incorrectly. Thank you.
Sir, I wanted to ask, can you explain the notation of...
Yeah, we'll do that next. That's the math part. But okay. I wanted to get the intuition first, because when you see the intuition, the math will suddenly click.